At the outset, I again thank Indian Academy of Science for inviting me to present this talk. Also, I thank BITS Pilani Goa campus for holding this meeting here. So I'll be talking today on modeling and control of large nuclear reactor. This nuclear reactor is first time in India. It has been commissioned at Tarapur and producing electrical power. So in a short time, I cannot discuss the entire work, of 5-6 years, half a dozen PhD students' work. So I will just touch some of the important points, what we have done in those work. And this is implemented, this reactor is at Tarapur, it is producing two of them, 540 megawatt. So basically, being an electrical engineer, control system engineer, I will be discussing the modeling of this reactor, how it is modeled. And this modeling is different from all other reactors which are there in India. There are 10, 15, 11. So that part I will touch. And then I will touch one important algorithm, the sliding mode control, the robust control technique, how it is implemented here. That this control technique is a very novel technique, is one of the most accepted robust control design techniques. It is invented in Soviet Union, in the then Soviet Union in 1950s. And then it was confined there until a paper in control transactions came in 1977. And it sparked research interest all over the world. And this has become a well-accepted technique of the robust control system design. This is so popular in IEEE Control System Society. There is a technical committee on this topic. And they are responsible to hold a biennial international workshop on this topic. So that I will also touch. And then certain simulation results on this reactor, and then certain references. So modeling and control, as I told, the control problem. What is the control problem here? The nonlinear model, how it is obtained, linearization, then a state space model of 70th order, 71st order differential equation, which is model. This is not, small reactor model, that is not sufficient, that kind of modeling. How this big model, the 70th order model, has been developed over several years by myself and my PhD students, that I'll be discussing. And then, as I told, the sliding mode control, how it is implemented in this reactor, and some simulation results and selected references. So this is the schematic diagram of the reactor, that the core part, then control rods, then the coolant, the heat is taken out to the secondary side, then turbine and all these things, electricity is produced. So basically, it is the Otto Hahn, I think the Nobel awardee of 1939 or 8, I'm not very, around that time. It is due to him that it is the fission. It is, chemist, 1938? Okay. It is the fission reaction that was invented by him, and it is the fission, due to that the power reactor is possible. The concept of power reactor. Electricity can be obtained from the nuclear reaction. So that was first invented by him, and then the power reactor concept came. So what is the nuclear reactor? A nuclear reactor is a device in which controlled fission reaction takes place. The fission reaction, it has to be controlled. That is the control problem. That is done in all nuclear power reactor. So typically, a nuclear reactor, neutrons are absorbed in the fuel. Uranium fuel is used for this reactor, which I'll be talking, which undergo fission, resulting into production of fission fragments, neutrons, other radiations, and release of approximately 200 mega electric volt energy per fission. One fission reaction, this much energy. So this is, as of June 2023 in India, 23 power reactors are operational, producing these 7.5 gigawatt approximately, besides 4 research reactors at BRC Trombay and IGCAR, and for isotope production and research. So most of the power reactors in India, pressurized heavy water reactor of capacities 220, 540, and 700 megawatt, using this as a fuel, heavy water, D2O. D2O is a moderator and deflector, and also heavy water as a coolant in this pressurized heavy water reactor. So two such units are operational at Tarapur since 2005-2006. And one 700 unit is operational at Kakrapara since 2023. Similar kind of concept, similar design, only it is 700, and it is little boiling is the limited boiling of coolant is allowed in 700, which is not there in 540 megawatt, which is at Tarapur Commission. There is no boiling, only pressurized water. The heat is taken by the coolant to the secondary side. So the dimension is basically this kind of why the control system engineers are interested to design controller for this kind of reactor. And this the physical dimension of a reactor. If it is roughly 25 times more than the migration length, the slowed down length and the diffusion length, then the no longer that concept of the small reactor will work. Means, I will explain little more. The category of this is called as a large reactor to be operated at flattened flux distribution produce electricity. What is the large reactor? The neutron production and absorption phenomena in one part of the core are not felt in other parts of the core. That's why the control system in one part will not work. Although you can control the global power mathematically, but in reality, it will not control the total power of the reactor. That is the basic problem. That's why this spatial control and several control systems are needed for this kind of reactor. This is coupled with non-uniform rate of production and removal of xenon is a species which is a fission product, which is very important, which I am coming. Why it is? Because it can absorb neutron. So xenon dynamics has to be included. So I will come to that, how the xenon is produced. So that's why it is necessary, the modeling and control of such a reactor, and not only the nuclear power precursor, also there are two products, that is the xenon and iodine, their dynamics are to be considered. And also it is a large reactor, that's why the whole reactor is divided into several zones. In this case, this 540 megawatt reactor, it is divided into 14 zones. It has been divided in other zones also, and then it has been found the simulation results with the benchmark results, which is a Sandia Research Lab, they published. So it is compared, and then it is found, but this reactor, the 14 division is all right. So reactor needs to divide several zones, each having own flux detector and reactivity control. So this is the reactor, the front hub and the back hub. It is 8-meter diameter and 6-meter long, this particular 540 megawatt reactor. So this is one of the such thing it is shown. And each zone is to be described by a set of equation, the rate of change of power, which is essentially the proportional to the neutron density, concentration of the delayed neutron precursor. When fission takes place, it splits into two, and they again decay neutron. So that is also controlling the dynamics of the reactor. That is known as the delayed neutron precursor. Then, among the various fission products, the xenon enjoys a special importance due to its large thermal macroscopic cross-section and long half-life. Large macroscopic cross-section, it can absorb neutron, and it can change the reactivity. So xenon has to be modeled. And the xenon is produced from the iodine immediately after the fission reaction. So iodine has to be modeled. And then the major portion of xenon is formed from the iodine, and only a small fraction results directly from the fission. But the major is obtained from the iodine. This is that reaction, the uranium-235, the tellurium, in a very quick time, less than a second, and then less than a minute iodine, and then 6.7 hours, iodine is converted into xenon, iodine, next. And then the cesium and then the barium, very stable isotopes, they are not of interest for modeling. So this is the formation of xenon 135 in a reactor and its decay. Now I'll come, what is happening in this reactor, why the control problem is very challenging, that what happens in this kind of large reactor, that increase, which is not happening in a small reactor. That's why small reactor, you can model by second order differential equation, one power equation and one precursor equation, which is not true here. Why? This is the reason for that. I will quickly go through those equations, how, but not very detailed discussion of those equations. An increase in neutron flux in one part of the reactor increases the rate of consumption of the xenon. If it increases by due to certain fueling, refueling, or disturbance or anything, and then what happens? The rate of consumption that increases, and its production through the decay of iodine will happen several hours later, so that the flux of the neutron gets another chance to increase further. And then it increases further. That's the net immediate effect is that the increase of the rate of consumption of xenon will further increase rate of consumption of xenon will further increase the neutron flux due to reduction in absorption of thermal neutrons. This process leads to continued decrease in xenon concentration and a steady increase in neutron flux. This may continue for several hours till the production of xenon from iodine becomes appreciable. So it takes several hours, 7 to 8 hours. And then again, the xenon, then what happens? The iodine produced, and xenon is produced from the iodine, and reverse process takes place, and xenon concentration start increasing, and flux is decreasing. So it is about 15 hours in one cycle. So total is 30 hours. What is known as the spatial oscillation. It was not known earlier. And if this oscillation is not controlled, if it is not stabilized, the whole reactor can blow up. So this was not considered. This is not to be considered in small reactor, but this is very important in the large reactor. This kind of oscillation. A lot of research have been done. What kind of oscillations, what are the different frequencies, magnitude, and all these things. So this is known as the spatial oscillation. I think it is also discussed here very briefly that you see the whole reactor, two parts, if one considers, and due to some reason, if the flux increases, then what happens? The xenon gets a chance. Initially, they're all in equilibrium. So xenon gets a chance to absorb those neutrons, and xenon decreases. And then xenon, not much xenons are available from the fission reaction, then the flux further increases. And this goes for, as I told, for some time, and then the xenon produced from the iodine, and after a few minutes, the flux tilting takes place. What is the meaning is that some part of the reactor will be demanded to produce large power, some part is a less power. So flux tilting takes place. And that tilting, it can exceed the design of the reactor, thermal capacity, a lot of other kind of design problems it can cause. That's why this kind of oscillations are to be controlled. So this is dealing with the spatial control of those, power. If we control every zone, then this kind of tilt will not be there. That is the idea. So what is this? This is the control problem of a large reactor. Maintain the reactor power close to the set point called the power demand. Maintain the power distribution closer to the desired power. Maintain the fractional zonal power close to their equilibrium values. This problem has been attempted by various approaches. This output feedback, there are two of them, multi-rate technique in control, that if you create a rate difference, that is a very important problem. Those who are in control system engineers, they know that control system has so much advanced, but there is an open problem. The static output feedback control, the stability of the system is not guaranteed. There is a paper in Automatica, 100 papers are referred by Peter Dorato, who was the chief editor of Automatica. And conclusion is that by using a static kind of output feedback, static output, you cannot stabilize. You cannot guarantee, although it is the simplistic structure, simple structure. So there is a technique called multi-rate technique. In discrete case, in continuous, it is not possible. So if you create a rate difference between the input and the output, then it has been shown that a arbitrary pole placement or eigenvalue placement of a dynamical system is possible using this kind of feedback. So that is called, these Tiwari, Sharma, Reddy, they are all PhD students. Tiwari was a BHC scientist, recently retired. In fact, the PhD first work started in 1990 with his PhD work. He is now joined one of the IITs as a visiting professor. He retired from BHC, and then other also did work on this. Sliding mode control is a very, as I told, the important technique which has been implemented this thing. So there I will talk. This this is that, the reactor is divided into several zones, and this particular reactor is, the control rod is not inserted. It is the JCC, zonal control compartment, and there is a water level. So by controlling the water level, the reactivity is controlled, and the fission reaction is controlled, and the flux is controlled, and the power is controlled. So this is the mechanism. This is this kind of reactor. So this is shown that there are this cylinder kind of 8-meter diameter, 6-meter long. So two tubes, two JCC are inserted one side. At the middle there are two, and other side there are two. So this 2 is divided into 2, so 4, and middle is 3, 6, and other side is 2. So there are total 14 zones. Water level is controlled independently, and that's why it's the multivariable control problem. There are 14 input and 14 output. Each zone is divided into 14, and each flux is detected by a flux detector. And so that they are now known as the output, and they are known as the input. So it's a large multivariable system, 14 input, 14 output, 70th order system. So powered their iodine concentration. So this is, in fact, this, to model this equation, it has taken 5 years. So I cannot speak in 5 minutes, but what is done here, the reactor is considered in 2 flux energy, phi 1 and phi 2, and their partial differential equation. So nodalization is needed, and then it is converted into ordinary differential equation, and then each zone, the reactor is divided different zones. So every zone is represented by their average values. There is no time, space dependent, it is time dependent. So that way, that is 2 group, and then further it is, I'll quickly run down, and the 2 group equation, and by it is converted into 1.5 group equation by some technique developed in Stuttgart Research Lab. My student was visiting, and then an effective 1 group flux for every zone. So there are 14 zones, so 14 flux, and 14 iodine, 14 xenon, 14 precursor, and 14 that reactivity, that the actuator dynamics. So there are, that's why 5 in every zone, 5 of them. So there are 70 differential equation, nonlinear equation, which is representing this reactor model. Then linearization is done, all these things is standard vary, and the linear model is obtained. They are the state variable, output variable, and input variable, and it is put in a state space model. Then this control, these are the different things. It is an unstable system, high order, possesses 2 timescale property. It is a stiff system. Some are operating very slow dynamics, some are very fast dynamics. So it is called the singularly perturbed system, stiff system. So control is more challenging. Then this, a few seconds that there are fast and slow modes. System response should be observed for hour to conclude the performance of a controller due to the xenon oscillation, and system is controllable and observable. Then there are various techniques. So this SMC sliding mode control technique, as I told, it is very simple in control structure, and it is one of the most accepted robust control design techniques. So there are sliding mode, discrete, because we have to implement through computer. So discrete sliding mode is proposed. Then discrete output feedback sliding mode control also is proposed. Then this concept of, these are the discrete output feedback control, various people have proposed. We have proposed the multi-rate technique of that discrete sliding mode control, and which is implemented. So this is the state space, the discrete model, and this is the discrete, multi-rate lifted system, the reaching law, and then the control is obtained. So this control, 3 simulations are carried out. One is the power maneuvering transient. That means how it is settling to a new demand from 1800 megawatt. That has been shown. Then initial power mismatch, if it is disturbed the initial power, how it is settling to the new power, the actual, the rated power, the equilibrium power. That will be shown. And if there is a disturbance is created, external disturbance, and then how it is sustained, that external disturbance, and the controller can perform again correctly. So these are the 3 simulations. This is one is that 1800 megawatt is the rated, the full power, and then 10 megawatt per second for 18 seconds, the power is reduced. And then it goes to settle to new value in actually in 1500 seconds, it goes to within 1.5, and 3000 seconds, it settles in within 1% error. The new demand from 1800, 10% megawatt for 18 seconds, it goes to 1640 megawatt. 1640 watt is electrical power. So one third of, nuclear power. It is one third of that is the electrical power. And this is the zonal power variation. Then xenon concentration, it takes several hours, 30, 40 hours, which is very slow. So when such a, tracking, the new demand is put, how the xenon, again, it settles to its new demand, new equilibrium value. That simulation is shown, and this is the global power, how the global power is controlled by adding the local power, the zonal power, the 1800, how it is goes to 1620, and then the actuator dynamics, the actuator, the control, how the control is. The control is the valve. The valve can open, -2 volt completely open, 2 volt completely closed. So that water level, by closing the valve, it is controlled the water level at the tube, which is controlling the reactivity. So this is plotted. Then tilt, as I told. The three kinds of tilts are important here. That is the axial tilt, side-to-side tilt, and the front-to-bottom tilt. That means there, the justified how control is good if the tilts are controlled. So tilts are plotted here, and it has been found the tilt, the top-to-bottom tilt, all tilts are almost, it settles to 0, and top-to-bottom tilts, it settled within 2%, which is the actual tilt also when it is designed the reactor. So this is the tilt is plotted, and then the global power, how initially there is an increase in the global power because the initial, there is a mismatch in the initial power, so there is a global power increases, but it settles to again the new values. Then there is a mismatch in the there is some kind of signal is added to the matched uncertainty, added to the control signal. Then how the different zonal power again settles to, it is increased to 0.01 voltage per second for 10 seconds, and then another 10 seconds it is decreased to 0. So such a disturbance, when it is created, a uncertainty, some signal, controls, some electrical signal is sent through the control, actual control, then that's why there is a change in the power, transient power, and then it settles to, again, its actual value. So these are the three simulations that are carried out, and other
Professor Mukhopadhyay, can we go to the summary slide?
Yeah. That's all, and there are several references.
Thank you.
Who have done PhD on this topic, and one of the article which is published in the world largest encyclopedia online, the EOLS publisher, we were invited to contribute an article there. So this is, let me check. Yeah, this is there's the largest volume, 400 print volume equivalent. So we were invited to contribute an article in this encyclopedia and many other IEEE transactions on nuclear science. Thank you.